This is a walkthrough of a further mathematics AS further statistics 1 paper. Question number 1. In a survey, 200 people aged 25 and older were randomly selected and asked how much time they spend on social media each day. The table below shows a summary of the results. So we've got like a two-way table here. The time spent on social media, whether that's less than an hour or more, and age groups 25 to 40 and 55 and older. NOAA carries out a test at the 5% level of significance to see if there is an association between age and time spent on social media. He uses the hypothesis H0. There is no association between age and time spent on social media. H1. There is an association between age and time spent on social media. He calculates the sum of the observed squared minus the expected, the observed minus the expected all squared over E, equal to 0.45 for this information. Part A, state the conclusion of the test, justify your answer. Well, to state a conclusion, we need a critical value to compare this test statistic with, and to do that, we need to calculate the degrees of freedom. So, even though you can calculate degrees of freedom in your head, always write down the calculation. So for a two-way table, contingency table like this, it's going to be the number of rows minus 1 times by the number of columns minus 1. So that's just going to be 1 minus 1, so it's 1. So we have 1 degree of freedom. So in our formula book, we need to look up chi-square tables, 1 degree of freedom and 5% level of significance. If we look it up, we'll get a critical value of 3.841. Now, if you've got one of the CG50 graphic calculators, you can also use your calculator to get the critical value. Now, if I look at my test statistic, that is a smaller value than my critical value. Now, the way that it works for contingency tables is that, or with any chi-square test, if your calculated test statistic here is less than a critical value, that means that the spread of your data from what you expect is quite low compared to this critical value. If it was bigger than critical value, then the spread of my data from what I expect, almost like the variance or standard deviation from what I expect, is going to be quite high. And that will tell us what type of conclusion we're going to come up with. So 0.245 is less than 3.841. That means that we're going to accept H0. In other words, there's no association between age and time spent. If there was an association, then these values would be a lot different to what we expect. So we can just finish with our conclusion, which is there is insufficient evidence, and we're basically just copying down what H0 or H1 is, to suggest insufficient word evidence to suggest there is an association between age and time spent on social media. Okay, right, let's move on to part B. So part B says, explain why having a large number of age groups may cause a problem when carrying out the hypothesis test. So I would say this is to do with the expected frequencies of a large number of groups being less than 5. So I'll put here, if we have a large number of age groups, we may have many groups with an expected frequency less than 5, and that would mean combining age groups. So you've separated out these age groups, and then you'd end up recombining them. Part C. J decides to take the same information and subdivide the age groups. She then uses the information in the partially complete table below to carry out a test at the 5% level of significance of the same hypothesis. Okay, so we've got some calculations that have been done here for our test statistic. And over here you can see we've now got 1, 2, 3, 4, 5 age groups when before we just had 2. Complete J's hypothesis test. State clearly the degrees of freedom and the critical value used in the test. Okay, so that means finding first of all the values that go in these two cells here, and to do the calculation we're going to have to work out the expected values. We've got the observed here, we just need to work out the expected. So that means finding the row and column totals from this table here from our observed frequencies. So first of all, we have a sum here of 92. I'm going to add all of these up here, and then this column here, this adds up to 108, and we only want to find a total for this row. We don't need to find the other rows because the rest of the table is filled in, and that's a total of 26. And then we have a grand total here of 200, because remember 200 people were asked in this survey. So we're going to work out the expected value for the 7 that's here. So I'll just write this E7, the expected value for 7. Now remember that we do the row total times by the column total divided by the grand total to find the expected value. So that's 92 times 26 divided by 200, and that is 11.96, and that's greater than 5, so we don't have to combine anything. And we're now going to find the expected value for the 19 here. That's going to go in this cell, and that is going to be, well, it won't go in that cell, but it will form the calculation for that. So E19, and row total, column total, so 108 times by 26 divided by 200, and that is 14.04. So again, this is greater than 5, so we don't need to combine anything. So now we do this calculation here. So we'll do the observed minus the expected all squared over the expected. So we're going to do it for this one here, 65 and older, less than 1 hour. So the observed, that was 7, minus the expected, that was 11.96. That's going to be squared, divide by the expected, and that's 11.96, and that becomes 2.0569, and so on. And then I'll do the same for this cell here, and that would be the observed, which is 19 minus the expected 14.04 divided by the expected 14.04. Oh, and that's all squared, and that's 1.77522, and so on. Right. Now we find the sum of all of those observed minus the expected squared over the expected. That will give us our test statistic. So we're going to add together all of the numbers in the table so far. So 0.47 plus 0.4 plus 0.02 plus another 0.02, and then plus 0.25 plus 0.21 plus 2.37 plus 2.02 plus the two values that I've worked out previously, so this one here and this one here. I could actually have just put the calculation part in here, but I'll put these numbers in since I've already done the calculation. So that will be 2.05, so on, and then plus the 1.752, and so on, and that will give me 9.56924, and it carries on. So that's our test statistic. Now we need to find our critical value. To do that, we need the number of degrees of freedom. So it's the number of rows and column minus 1 from both of those and times together. So we've got 5 rows, so 5 minus 1 times by the number of columns, that's 2 minus 1. So that will give us 4 degrees of freedom. So my critical value will have 4 degrees of freedom, and we're testing at the 5% level of significance. From the formula book or your calculator, that gives you a critical value of 9.488. Now you can see that our calculated value of 9.56924 is greater than our critical value. That means that spread is too much to accept H0. So we reject H0, and our conclusion is different to before, and that is that there is sufficient evidence to show there is an association between age and time spent on social media. Between age and time spent on social media. Social media. And part D. State, giving a reason, which of the conclusions in part A and part C you believe to be the more reliable. So I think part C would be more reliable because the data has been separated, or the age groups have been separated or divided into smaller groups. So you can see more of what's going on. So in the previous part of the question, we only had 2 age groups. One was 25 to 54. So basically 25 to 54, all of these 3 groups here were all clumped together into one. So if there was some association between some of those ages, they would have been lost because they all clumped into one group. And then the second group was the 55 and over. So all of this information here was clumped into another group. So any patterns would have been lost by that grouping. So part C, that data would be more reliable. Question 2. The discrete random variable x has this probability distribution here, where the outcomes are 2, 3, 6 and 11, and the probabilities are 1 over 50, A, 1 over 25 and B respectively. The discrete random variable y is equal to x squared. Given that E of y equals 50.3, part A, find the value of A and the value of B. Now, since we have y is equal to x squared, that means that E of y is equal to E of x squared. And we're told that that's equal to 50.3. So we know how to work out E of x squared. We take each outcome, we square it, and we multiply the probability. So we've got 2 squared times by 1 over 50 plus 3 squared times by A plus 6 squared times by 1 over 25 plus 11 squared times by B, and that's equal to 50.3. Now if I tidy that up, that will give me 9A plus 121B is equal to 48.78. So here's my first equation. Now the second equation we get from the fact that the sum of the probabilities is equal to 1. So the sum of P's, all the probabilities, is equal to 1. So that will be 1 over 50 plus A plus 1 over 25 plus B is equal to 1. That equation can be tidied up a bit, and we'll have A plus B is equal to 0.94. So there's my second equation. What we're going to do now is to solve these simultaneously, and I'm going to do it by the calculator. And if I do that, I will get A is equal to 0.58 and B is equal to 0.36. Part B. Find the probability that 9 minus y is greater than 0. So the first thing I'm going to do is to write down what the values of y are. And I'm just going to put it on the top row of this table. So y, remember y is generated by doing x squared, so we'll have 4, 9, 36 and 121. And what I want to do is to do 9, take away each value of y and see if it's greater than 0. So if I start with this first column here, if I do 9 minus 4, yeah, that's definitely greater than 0. So I want that probability. So I want this column here, or the probability actually 1 over 50, but I'll just put that column. If I go to the second column here, and I do the same thing, 9 minus 9, so 9 minus the value of y, 9, well that's not greater than 0, so I don't want that. And in fact, if I do 9 minus any of these other values, they're all going to be negative, so they're not going to be greater than 0, so it's just this probability here. So I could write my answer like this for part B. The probability that 9 minus y is greater than 0 is actually equal to the probability either that x is equal to 2, or you could write the probability that y is equal to 4. They're both the same thing. Whichever one we write down, the final answer is going to be just 1 over 50. It's the only probability that satisfies the conditions that are given. Right, moving on to part C. Let's see what it says for part C. So the independent observations x1, x2, x3 all the way up to 120 are taken. The random variable t represents the total number of these 120 observations that are even, and we need to find the mean and the variance. Well, the first thing we need to do is to work out what type of distribution this is. We've got independent observations. You could think of those as like independent trials, and there's 100 of them, and there's a fixed number of trials, and I guess I could work out the probability that an observation gives me an even number. I can use the table for that. So this is going to be a binomial distribution. The random variable t is binomially distributed. There's 120 trials, and I want to work out now the probability that observation of x is even. So that's going to be this column here, that's an observation of x that's even, and this one here, that's an observation of x that's even. So the probability of success is fixed, and that is what we get when we do 1 over 50 plus 1 over 25. So 1 over 50 plus 1 over 25, and if we add that together, we'll get 3 over 50. So my probability of success is 3 over 50. Right, so here is my binomial model, and in the first part of part C I want to find E of t. Well, that's just the mean, and the mean of a binomial distribution is n times p, so that'll be 120 times by 3 over 50, and that's 36 over 5, or 7.2. Right, so that's my mean. The next thing we need to do is to calculate the variance of t. Now, the variance of a binomial distribution is np times by 1 minus p. So in this case, it's going to be np, that's 7.2, times by 1 minus p. So 1 minus 3 over 50, which is going to be 47 over 50. And that gives exactly 6.768. I could round that to 3 significant figures, but I guess there's not much point, so I'm just going to give the full answer here. And then part D, what's part D asking us? It says, find using a suitable approximation the probability that t is greater than 10. Now, to decide what a suitable approximation is, I need to look at n and I need to look at p in this case. Well, the number of trials, the number of observations is large. Normally when it's greater than 50, we say that the number of trials is large. And we need to look at the probability as well. Now the probability here is 3 over 50. Now 3 over 50 is actually the decimal 0.06. So P is small. So since n is large and P is small, that means that we can approximate our binomial distribution with a Poisson distribution. So let me write that out. So we'll take our binomial distribution of 120 and 3 over 50 and approximate that with a Poisson distribution where the value of lambda is the mean, and that's 7.2. I guess I didn't finish my sentence off from before, didn't I? So since n is large and p is small, we can approximate using a Poisson distribution. Let's carry on over here. Poisson distribution, which is what I've done. So I want to find the probability that t is greater than 10. So I'm going to say my approximation is this Poisson distribution with 7.2. Then on my calculator I can work out the probability that it's greater than 10. That's going to be 1 minus the probability that it's less than or equal to 10. Now that's going to be 1 minus 0.88667. So let's do that, and that becomes 0.11332. Now I'm going to round it to 3 significant figures, so let me write it down over here. So 0.1133233 and so on. So 3 significant figures is going to be 0.113. So 0.113, and I'll just put here that this is 3 SF, 3 significant figures. Let's just highlight that. Question 3. A hotel has 30 rooms. The manager models the number of empty rooms each Friday night using a binomial distribution with n equal 30 and p equal to 0.08. So that's probability. I guess the room is going to be empty. The manager recorded a number of empty rooms in the hotel each Friday night over a period of 80 weeks. And here we can see the number of empty rooms and the frequencies at which they occurred. So from no empty rooms all the way up to 6 or more empty rooms. The table below shows the expected frequencies using the manager's model. So number of empty rooms along the top and the expected frequencies along the bottom. Part A, find the value of R and the value of S. Okay, now for both of these values here, we need to work out the expected probability and then times that by 80, because basically he's measured it or took a sample over 80 weeks. So first thing we want to do is let's start with 2 empty rooms, find the expected probability. So we've got a binomial model, so 30 and 0.08, and for R we want to find the probability that x is equal to 2, that there were 2 empty rooms, and that is 0.2696 and then what we want to do is times that by 80, and that gives us a value of R as 21.5684. Now since the other values have been given to 2 decimal places, I will give my values to 2 decimal places and state that as well. So R equal to 21.57, that's 2 dp. So we'll do the same for S now. So for S, we're looking at the probability for 5 or more empty rooms. So the probability that x is greater than or equal to 5 which is going to be 1 minus the probability that x is less than or equal to 4, and then once we've found that value we're going to times that by 80. So we've got a probability of 0.0873. So when we times that by 80, we'll get a value of S as, let's times that by 80 in the calculator, 6.9889. So again, I'm going to give S to 2 decimal places, so that'll be 6.99, so 2 dp. Part B. Stating your hypothesis clearly. State or test the manager's model at the 5% level of significance. So we always start with H0 and H1. So H0 is going to be that this binomial with 30 and 0.08 is a suitable model, and H1 is going to be that the binomial with 30 and 0.08 is not a suitable model. Okay, so from there we need to calculate our test statistic, x squared. Now, to calculate x squared, I prefer to use the formula, the sum of the observed squared over the expected minus n, as opposed to the sum of the observed over the expected all squared over the expected. I find this quicker and easier to work out than doing this form. So let's now write down what's that is going to be. Okay, so equal to, so we've got a big long sum to do, so we'll our observeds are all here, our expected are all here, and our S are here. So my first observed is 14. Observe squared over my expected for 14 was 6.56, plus the second observed was 18 over the expected for 18, which was 17.11. Then my next observed was 22, that's squared over the expected of R, that was the 21.57 I worked out, plus 11 squared over 17.5, plus 10 squared over 10.27, and then plus 5 squared over my value of S, which was 6.99, and that's all of the observed squared over the expected, so I want to find the sum of those, and then I'll minus 80. Okay, now in this question we have two n's, don't we? Little n is the n from the binomial 30. Big N, the number of observations, is 80. Right, doing this calculation, I get a value of 11.480, and I now need to look up my critical value. So before I do that, I need my degrees of freedom. So that's the number of columns minus 1, 1, 2, 3, 4, 5, 6. So 6 minus 1. Now I've not had to combine any columns because there were no expected frequencies less than 5. I haven't mentioned that, but none of these, that's the two that I worked out, none less than 5, so I don't need to combine any cells, otherwise it would have been less than 5. So from the formula book, I can look at my critical value, 5 degrees of freedom, and it's 5% level of significance. So from the formula book or calculator, that would give me a critical value of 11.070. So now I'm going to compare my test statistic, which was 11.480, and compare that to my critical value, and it's actually greater than the critical value, isn't it? So anytime our test statistic is greater than the critical value, that means we're going to reject H0, which means that our binomial with 30 and a probability of 0.08 is not a suitable model. Part C. Suggest an improved model for the number of empty rooms in a hotel each Friday night. Well, our original model, yeah, happy with the 30 because it's 30 rooms, but don't know where this probability came from, 0.08. You know, where did the manager get that probability? So to improve the model, we'd want to estimate P. And our formula to estimate P is the sum of the frequency of R times R, or R times the frequency of R, divided by little n times by big N. And I did mention this before here. So let's estimate P then and see what we get. So this is my R row here, and this is my frequency of R, and basically I want to times them together and add them up. Right, so 0 times by 14, well that's just 0. 1 times by 18, so that's 18, plus, because we're finding the sum. 2 times by 22, so we're adding 44. Then plus 3 times 11, 33. And then to that, we're going to add 4 times by 10, so add 40. Then add 25, so that's it. And then we divide that by n times by n. So little n is 30 times by big N, 80. Now when we do this calculation, we'll get an estimate of P as 1 over 15. So an improved model would be binomial with 30, but using a probability of 1 over 15. Now if we did have this improved model here by estimating P, that means we'll get different values for all of these expected frequencies. We'll get a different value for our test statistic. We'll get the same degrees of freedom, but we could come up with a different conclusion here. Rather than rejecting H0, we may end up accepting H0. Question 4. An office has a photocopier and a printer. The photocopier and the printer break down independently. The number of breakdowns per month for the photocopier follows a Poisson distribution with mean 2.4. The number of breakdowns per month for the printer follows a Poisson distribution also with a mean of 1.6. Part A, determine which machine is more likely to break down exactly twice in 1 month. So we have our photocopier, and it's the number of breakdowns per month. It's a Poisson distribution, mean 2.4. And for the printer, again, it's the number of breakdowns per month. It's a Poisson distribution, a different mean. And what we need to find is the probability that one of all the others going to break down twice in a month. Now I'm going to use X as the random variable for the photocopier and Y as the random variable for the printer. So starting with the photocopier, so that's a Poisson distribution with a mean of 2.4, and we want to find a probability that there are exactly 2 breakdowns in a month. From the calculator, that's 0.26126, and then for the printer, that's a Poisson with a mean of 1.6, and probability that Y is equal to 2, and that gives 0.25842. Now since one of these probabilities is greater than the other, so since 0.26126 is greater than 0.25842, that means the photocopier is more likely to break down. Is more likely to break down. Part B, work out the probability that both machines break down at most once in 1 month. Now, at most once is going to be this type of probability, at most once. And then it says both machines break down. So it's one machine and the other, and we're told that they break down independently. So that means we can multiply the probabilities, because it's one breaking down at most once and the other breaking down at most once. So it's going to be the probability that the photocopier breaks down at most once, and or times the probability that the printer breaks down at most once. So those probabilities are 0.3084 times by 0.5249, and that will give 0.1618, and I'll give my answer to 3 significant figures, so 0.162, that's 3 SF. Part C, in a randomly selected month there were 4 breakdowns. Find a probability that in this month the photocopier broke down more than the printer. So you could actually think of the wording of this as like this: given that there were 4 breakdowns, what's the probability that the photocopier broke down more than the printer? And this is an example of conditional probability, where the probability of A given B is equal to the probability of A and B over the probability of B. In other words, it's going to be out of the fact that there were 4 breakdowns. Right, so let's have a look at what this is going to look like. So if the photocopier is going to break down more than the printer, and there's been 4 breakdowns, either the photocopier breaks down exactly 4 times and the printer doesn't break down, or the photocopier breaks down 3 times and the printer breaks down once. There aren't any other combinations where the number of breakdowns of the photocopier is more than the printer. Any other ones, that's either going to be the same, or the number of breakdowns from the printer will be more. And we divide that by knowing that there were in total 4 breakdowns. So we can add our 2 lambdas together for this part here, the sum of independent variables. So this bottom bit actually is going to have a Poisson of 2.4 plus 1.6, so it's going to have a Poisson of 4. Right, let's write down all of the bits of this. So it will be 0.1254 times by 0.2019, I'm giving these all to 4 decimal places, plus 0.209 times by 0.323, and that's all going to be divided by, so I need to change my Poisson to 4, and the probability that with Poisson equal to 4 that x plus y is equal to 4, and that's going to be 0.1954. If we do that calculation, we'll get 0.4750. So to 3 significant figures, 0.475. Okay, so lots of bits to watch out for in that calculation that could easily be missed. Part D. Test at the 5% level of significance whether or not there is evidence that the rate of breakdowns has decreased following the repairs. It would help if I read this bit before. A repair company carried out repairs on the photocopier and the printer. Following the repairs, there were a total of 3 breakdowns in 2 months, right? 3 breakdowns in 2 months, 5% level of significance, whether there's a rate that the number of breakdowns has decreased. So since I am dealing with 2 months, I'm going to set lambda equal to 8, the rate of breakdowns in 2 months. And since I'm looking to see if it's decreased, I'm looking to see whether the rate of breakdowns in 2 months is less than 8. Now I'm going to use T to stand for the total number of breakdowns. That follows a Poisson distribution with 8, rate of 8 over 2 months. And because it's a lower tail test and I observed 3 breakdowns, I'm going to work out the probability that x is less than or equal to 3. Doing that on my calculator, I get 0.04238. Now if I have a look at that value here and compare it to 5%, so 0.04238, that's less than 5%. Since it's less than the significance level, that means reject 80. And if I'm going to reject 80, my conclusion is going to be this: there is evidence to suggest that the number of breakdowns has what? Has decreased. Number of breakdowns has decreased.